Thank you very much. First of all, I should say hello to all. I think that for those from Colombia, I should say good morning. And I thank Dr. Roberto Marin and his colleagues for giving this opportunity to me. The title of my presentation is Probabilistic Analysis of an 80,000 square meter landslide in Shiraz, which is a city in Iran. And this is not a work just by mine alone. I had some colleagues, Dr. Falamaki, Dr. Ali Shafiee from California, and one of our master's students, Mr. Farzad Arjmand. First, as an introduction, well, many landslides occur all around the world every year, imposing adverse effects on people, societies, and surrounding environments. And according to a statistical analysis by Petri 2012, at least more than 32,000 people were killed from 2004 to 2010 due to non-seismically triggered landslides, where the landslide causes can be categorized to natural, anthropogenic, and a combination of both. The major natural causes are slope saturation, the seismic activity, and the volcanic activity, and the activities such as excavation at the toe of a slope, adding surcharge to the crest of a slope, changing drainage patterns, destroying vegetation on hillsides, and construction belastings are among those examples of such human disturbances that could trigger landslides. And according to one of the United Nations manual, UNISDR 2017, unplanned rapid urbanization, poor construction quality, and weak land use management are some of the most significant underlying drivers that increase the level of the risk. And sometimes a combination of both natural and human-induced factors is responsible for triggering landslides. And our research was about a large landslide that occurred in the Shiraz city. It's a district which is called Mansurabad, but the city is called Shiraz. It's a mega city in Iran. Due to the increase in population and development of the city toward the mountains, the potential for landslide has been increased in recent years. The purpose of this study is to conduct a comprehensive study on this landslide so that the basic parameters of shear strength of formation layers containing marlstone and limestone can be determined and compared with field study and back analysis. Well, first of all, I should talk about a bit about the study area. Shiraz is the capital of Fars province in the southwest of Iran with a population of more than 1.5 million. The city is surrounded by folded and fractured mountains composed of sedimentary rocks. And the rapid population growth of Shiraz during the last 3 decades and the lack of land have resulted in construction on hillsides. This migration to higher elevation has significantly changed the environment and geomorphology of these mountains and disturbed the horizon view of the city. In recent years, several landslides have caused a very severe concern. So our study is not the first landslide. We had lots of landslides before too. For example, here on the February 2016, following a moderate rainfall, several marlstone blocks, as you can see in this photo, fell down and blocked a street. Here on July 2018, you can see a landslide occurred. You can see the slip surfaces here, and this is a residential building. A landslide occurred with and the area covered was about 44,000 square meter. And this is on the Psalm 2018. This is a residential building which was built near the mountain slopes. You can see this photo. I took this photo personally from the top. This is the roof of this building, and it was punctured. It was, you can see the roof is punctured due to the rockfall. So several huge rockfalls occurred, and it punctured the roof of this building. And this is a video from the May 2021. This is a mountainous road in the belt of the Shiraz. Watch this video, please. Well, and in this Google Earth image, you can see the location of recent landslide in the vicinity of the study area. Here, the stars are the location of each landslide. You know, I showed some pictures from July 2018, December, February. And here in this paper, we studied a landslide, a large landslide, which was the largest among all of them, which occurred here. And as you can see, this is the Shiraz. These are the residential buildings, and here this is the mountain, and this is a road, the mountainous road under construction, the road that you viewed in the previous video. So I'm going to talk about this landslide here. On July 15, 2020, a large landslide occurred adjacent to the road construction site and very close to residential buildings. You can see here, this is the residential building, and this is the, you can see these black lines. This is the territory of the landslide that occurred. And it's at the top, it's very, very close to the residential buildings. This is the sliding zone. These are 2 point A and B. We compare two images, one before the landslide, the other one after the landslide, and we saw that the point A moved about 70 meters and point B moved about 90 meters due to this slide. Here, this is the crown of the failure zone. You can see some fractures, some transverse fractures here from the top on the crown. And also you can see here some, white dots here. There are lots of white dots here. These white, dots, these white points are some planting holes that were dug and they were kept empty. Well, according to the local media, 40 homes were evacuated immediately, and fortunately, no injuries and deaths were reported. The area covered by the landslide is estimated to be around 80,000 square meters based on the satellite images, which is the largest landslide in this area. And here, this is a video, I took this video. I'm here at the top of the landslide mass, and at the top of the sliding mass. And you can see here the transverse fractures. Let me play this video. This is at the crown of the sliding mass. You can see parallel fractures. You can see here, this is the road, the mountainous road under construction, which passes through the toe of the sliding mass. Some of these fractures were as deep as 10 meters. So we believe that the depth of the sliding mass was about 10 meters. And you can, here at the top, you can see the residential buildings. Well, and these are, I think, again, another video. Well, I think I should move to the next slide here. This is another video. These are the rock blocks that were moved due to this landslide. And these are the main escarpment that was occurred, that was formed due to this landslide. And again, these are some video, these are the blocks of the rock blocks which was formed due to this movement. Well, and you can see these are some photos. This is the escarpment that was formed, and these are the the sliding rock masses. And you can see here a bench. We looked at the Google Earth images, and this bench was moved about 229 meters. And this interesting photo is from the toe of the sliding mass. Here we had a ground heave at the toe of the sliding mass. So it was from the crushed marl stones or crushed marls that they heaved about. They had a heave at high as 5 meters at the toe of the sliding mass. Well, the average slope of the sliding zone is about 11 degrees. However, so this is not a very steep slope. It is a mild slope. However, there exists some completely stable slopes with a slope angle of about 28 degrees, just 1 kilometer away from the landslide. In this study, we gathered information and collected data pertaining to the study area. We made several field and laboratory tests, such as the Schmidt-Hammer test, unconfined uniaxial compression test, the XRF and XRD tests. The joints configuration and asperity were measured, and next, all the data were used to model the landslide in a computer program. The limit equilibrium, the limit equilibrium method was utilized to investigate the stability of the slope in a program. Map, you can see the geological characteristics. This red circle is the landslide location. It was occurred in a geological formation which is called the Asmari formation. And this Asmari formation is located in the in the Iran. We have a very famous mountainous belt which is called the Zagros Fold and Truss belt. These are a row of mountains. And this Asmaric formation is made up of carbonate formations and quaternary sediments. This formation contains a strata of limestone, dolomitic limestone, random marl layers, numerous tensile and shear joints can be observed around the sliding zone. You can see here, you can see some of these joints here in this figure that due to existence of these joints, the rocks were divided into several blocks. Two sets of perpendicular tensile joints are obvious in the rock mass, which have created relatively regular rock blocks. The space between the joints is filled with soil and weathered materials such as marl and clay. Here in this figure, this is an excavation cut very close to the landslide location. Here you can see, I said, two perpendicular joints. These are some near vertical joints, and there was also some horizontal joints. And you can see, for example, here at the middle of these excavation cuts. And here, this is a zoomed photo from the vertical joints. These red lines are the the left boundary, and the right boundary of these vertical joints. And this is a pen. You can see that these vertical joints has a width of about 20 centimeter, and they are filled. They had some infilling. They were filled with clay soils and very highly weathered marls. And this, you can see here in this figure, the variation of marl characteristic with time due to the weathering. At the top right here, A, this is the marl layer, which is slightly weathered. You can see here, it has just some very few fractures and joints here. Here at the left, B, is this is the same marl layer, but it is at a later time. So it's weather moderate. You can see that the fractures and the joints are get wider and larger. And here at the time passed, this is a highly weathered marlstone here, and you can see that the marl is really, it's highly weathered, and it's turned into the soil. It's in fact it's a soil, not a marlstone. And this is a side view here. Here this is the crown of the landslide. These are the landslide mass, and the point of this photo is that, as you can see, these are some bedding plains, and we measure the tip of these bedding plains about 15 degrees. And as I said before, the average slope of this, here the average slope was 11 degrees. So we had here the unfavorable layering of the geological layer, and this unfavorable layering had a very, very important role in occurrence of this landslide. And I want to talk about a bit about the climatic characteristics of the region. The landslide occurred in a hot summer day with a maximum temperature of 39 degrees centigrade and no precipitation in preceding 2.5 months. Hence, the water flow has no direct influence on the occurrence of the landslide, but we believe that the variation in the rainfall regime in 2 preceding years has had an unavoidable effect by enhancing the weathering rate. We believe that weathering had a significant impact on occurrence of this landslide. The annual long-term precipitation of Shiraz is about 316 millimeter on average. But in the previous year, in the 2020, the annual precipitation of about 416 millimeter, which is about 32% higher than the long-term record. And since the materials of the sliding zone mainly consist of soluble carbonate rocks containing lots of joints and cracks, it would be likely that the increase of the amount of rainfall leads to the development and expansion of these joints and provides the geological preliminary of this hazard. In addition, as I said before, and as I showed in the Google Earth image, hundreds of holes have been dug all around the sliding zone for planting purposes in the past few years, with many of them left empty. These holes would accelerate the infiltration rate into the cracks and joints and reduce the shear strength of joints and parent rock. Well, we decided to use the Barton-Bandis failure criterion. It's a famous failure criterion for rocks to model the shear strength of sliding block. This is the failure. This is the equation here. JRC is the joint roughness coefficient. JCS is the joint compressive strength, and phi sub r is the residual friction angle. Barton in 1982 presented a chart for determination of the JRC, the joint roughness coefficient. Here we should, if this is a length of profile, the horizontal axis is the length of profile, and the vertical axis is the amplitude of asperities. You can see here, this is amplitude of asperities. So the geometries of 14 joints were measured in the field, and we used a ruler. A ruler was laid over the joints, and multiple high-quality photos were taken from a side view using a 12-megapixel camera. Then the photos were exported to AutoCAD software, and the joint's asperities depth was measured as accurate as possible. Our experience showed us that JRC values include so much uncertainties, and assigning a single value to an 8-hectare area is totally unreasonable. So, we use a probabilistic manner. The average value of JRC was 15.8 with a standard deviation of 4.8. And we also made several tests, both in situ and in laboratory. First, we had a Schmidt hammer, the N-type Schmidt hammer. So several N-type Schmidt hammer tests were performed at 12 locations of the rock mass in the project site. The measured Schmidt hammer rebound values were converted to compressive stress based on the following procedure. First, we convert the Rn, which is the N-type hammer rebound value, to the RL, which is the L-type hammer rebound value, using this equation presented by Aydin and Basu 2005. Next, some of the Schmidt hammer tests were performed horizontally. So the value of those tests were converted to downward valley values using the table presented in the paper of Barton and Chubby 1977. Second, we used these two equations. The above equation, it was presented by Deere and Miller 1966, and the bottom equation was presented by Azimian 2017 for Shiraz rocks. Here JCS is the compressive strength and RL is the Schmidt-Hammer, the L-type Schmidt-Hammer number, which was obtained from the previous steps, and gamma is the rock unit vector. Furthermore, the 3 uniaxial compressive strength tests were performed on the limestone sample driven from rock cores, and using all this value, we obtained an average value of the uniaxial compressive strength to about 33 megapascal with the standard deviation of about 5 megapascal for the limestone rocks in the study area. And a direct shear test was also performed on the thin weathered marly clay filling. This is the Moore column equation. So these marl clays had the friction angle of 10 degrees and a cohesion of about 20 kilopascal. Determination of strength parameters of marly layers is of great importance because it seems that these layers had influencing effect on the occurrence of the landslide under study. Moreover, the marly layers are found in various regions of Shiraz. For example, here in this photo, this is a highway in Shiraz, and you can see this highway is excavated in marly layers. And this is a very, very, high excavation. The height, I think it's about 20 or 30 meters. So the determination of the characteristics of these marly layers are very, very, very important. We also made some XRF tests. You can see here the results. For example, this is the CaO, calcium oxide, which was included about 50%, and it was also about 40% LOI. LOI stands for loss of ignition, and it can be attributed to the release of carbon dioxide at temperatures up to about 900 degrees. So this XRF results shows that the calcite mineral is an essential mineral in these marly layers. And here the results of XRD test, you can see that in addition to calcite, we had quartz and illite minerals here at this layer. And this is the SEM photo in 2 different scales, and the calcite minerals are obvious in this photo. And then we try to use a numerical modeling. We use the slide software, which applies the limit equilibrium method as well as the probabilistic approach used for the stability analysis. So we use the probabilistic approach. So you can see these are the different values of the Barton-Bandis criterion. And here mu is the average value or the mean value, and sigma is the standard deviation. We entered both the mean and the standard deviation in the software. We used 3,000 randomly selected samples in the probabilistic analysis. You can see this is our model. We saw that we had 2 marly interlayers, one at the depth of 2 meters and the other one at the depth of 10 meters. We back analyze. It means that we try to, here, at the landslide, when the deformations are very large, we have a residual state, and at the residual state, the cohesion is equal to 0. So the only parameter that we were seeking was the residual friction of these marl layers. So we back analyze, we change the residual friction of these marly layers, and to find the time, the place where the mean factor of safety is equal to about 1. And you can see here, this is the mean factor of safety of equal to 1. And the resulted value of the residual friction angle for this marly layer was about 6 degrees, which was about 4 degrees lower than the peak friction angle that was obtained by direct shear test. As I said in the previous slide, in a direct shear test, the value of the peak friction angle was 10 degrees. And this is a sensitivity analysis that we performed. You can see this red line, which is the JRC, has the most significant influence on the factor of safety. And next, these gray lines, the residual friction angle has the most significant impact. And as the conclusion, well, the identification of the physical and mechanical characteristic of the Asmara formation seems crucial, since this formation has various outcrops in the Zagros regions. And owing to the increase in significant landslide in Shiraz in recent years, we believe that the decision makers and stakeholders should take benefit of the expert opinion and consider the safety issues as the first priority. And thank you very much for your attention.